In this video, I want to take a look at some related rates problems. Now, related rates problems in calculus can be a little bit difficult at times in the setup of them because there's not always a cut and dry one-step philosophy to do all of the problems. A lot of the issues that arise when you're looking at these related rate problems arise when you're out of the wide variety of different geometric setups that show up in these problems. And so what I want to do in this first video is look at just that, just setting them up, looking at what information is given to you, being able to get a diagram, and then find the relationship, the appropriate relationship for the different variables that are in the question. And so on the screen you can see A through D. These are general steps that if you were going to actually solve the problem, you would want to follow all of these. There would be some more to come afterwards. But for right now, I'm going to focus mainly on just parts A, drawing the diagram and getting everything labeled, and then finding the relationship between the variables in that diagram. So I'm not going to worry about writing down my rates. We'll talk about them. We can point them out, but we don't need to write them down at this point. The main objective of this first lesson, this first video, is going to be able to get a diagram and get the relationship, and we'll worry about solving the actual problem in a later video. And so I just want to walk through a couple situations. Like I already mentioned, these are not all of the possible situations that can show up. These are just three of the common ones that we or you might see throughout your calculus class when it comes to related rates. And so for the first problem, we have a ladder 25 feet long is leaning against a house. The base of the ladder is moving away from the house at a rate of 2 feet per second. How fast is the ladder's top moving down the wall when the base of the ladder is 7 feet from the house? Okay, so a lot of information here to unpack. I've already drawn a diagram of what's going on, but what's happening, just to give a quick overview before we get into it too far, is in this, the base of the ladder is moving away from the wall to the right there at the given rate of 2 feet per second. What the question wants us to do is find out how fast the top of the ladder is falling. So you're given quite a few numbers here. The ones that I want you to focus on for right now are the ones that only have one unit involved. So when you see something like 2 feet per second, that's going to be a rate. We can see that we have feet, 1 unit per another unit of time. So we're not going to worry about that because rates aren't going to go on the diagram. And even the 7 feet there in the question, that's not going to go on our diagram either, because that's going to be a number that we use later on. So really the only thing that we need to concern ourselves with of getting on our diagram is the fact that the ladder itself is 25 feet. And so we can go ahead and put that on here. Now, when it comes to getting the rest of the diagram labeled, we can see that we're going to have some distance from the base of the wall to the base of the ladder. We're going to call that x. Now, the variables and what you call them doesn't overly matter as long as you're consistent and you have things labeled. And so you do want to keep in mind or have somewhere that x is the horizontal distance from the base of the ladder to the wall. And then we also have y, which is the vertical distance between the top of the ladder and the ground. And so we want to be able to come up with a relationship between those two variables. Those are the two that are in question. Even if you go back to the problem, right, the rate that's given to you is the change in x there. It's how fast that ladder is moving away from the wall. That would be your change in x. And then we want to know what the question is asking us is how fast the top of the ladder is falling. That's going to be our change in y when we're given a specific distance to plug in for x. And so this one is fairly straightforward, just in the sense that we have a right triangle here. The wall and the ground form a right angle, and so the relationship between x and y is just going to be x squared plus y squared equals 25 squared, the Pythagorean theorem. And for right now, that's where we're going to stop, right? We have our diagram, it's labeled, we've noted what x and y are, and we have a relationship between the two. Okay, so moving on to another situation that's fairly common is that we have water running into a cone-like tank at a rate of 9 feet cubed per meter, right? So not only does it have the word rate there, but we also see the units are a change in some kind of physical length or a radius in this case per time unit. So multiple units are there. So that 9 feet cubed per minute is not going to go in our diagram, but it's worth noting that this is a volume, right? So this is these units here are of volume, and so we have a rate for which our volume is changing, so we should expect to see volume as one of our variables in our final equation. And so then we're told that the tank stands point down, drawn that, has a height of 10 feet and a base radius of 5 feet. And so I've got those labeled here in purple. So we got 10 feet and then a radius of 5 feet. We want to know how fast is the water level rising when the water is 6 feet deep. And so how fast the water level is rising is referring to the depth. So this water level would be the depth, which I'm going to go ahead and label as h, just because it's very similar. So this would be my height. I see that as the height changing. And then I have this radius as well. And so what I want to do is I want to have the volume in terms of, so when we look at the equation that we can start with, we have that the volume is 1/3 pi r squared times the height. So that would be for the volume for any given cone. And so what we have here is we have volume in terms of both the radius and the height. And so this is where you do want to take a little bit of time to look at what the question is asking you. We want to know how fast the water level is rising, so we want to know the depth when we're given a certain height. And so what we can control in this problem is the amount of water that we're putting in, the volume. And so we want to get the volume in terms of the height. And so we can see here that if we take these two, where this is 10 and 5, and then we have our height and our radius, these are going to be similar triangles, and this is going to be something that shows up quite often for us in these problems. And so from there, what we can do is we can say that 5 over r is equal to 10 over h, our height. So we can relate those sides to one another using similar triangles. And then from there we can cross multiply, and so we get 5h is 10r. Now remember, we want to get the water depth, and so we're looking to get rid of r in this case. And so I want to get r in terms of the height, and so I'm going to divide through by 10 and get that the radius is a half of the height. And so then this is what I can plug in here to my volume to be able to get volume in terms of just the height. And so this volume would then equal 1/3 pi times a half the height squared times the h. It is worthwhile, technically from there we have volume in terms of height. and we could stop there. It's just, we're going to do more. I'm not showing you what that more is yet, but I'm going to go ahead and just tell you that it's a little bit easier to do the next steps after this if we've got a little bit more simplified of a problem. And so we can simplify this to a third pi times a fourth, the height squared times the height again, which simplifies further to give us 1/12 pi times the height cubed. And so this would be the final relationship that we want, where V is the volume and H is representing the depth of the water. And we'll stop there for now. All right, and then just one more. We have a man 6 feet tall. He's walking at a rate of 5 feet per second towards a street light, which is 16 feet above the ground. At what rate is the length of his shadow changing when he is 10 feet from the base of the light? And so lots of numbers here to break down. We have that the street light is 16 feet. We have that the man is 6 feet tall. Once again, the rate of 5 feet per second, that does not go on our diagram. We will use that at the later point. And so then what we have is the question itself. We want to know the rate of the length of his shadow. So we need something that is his shadow right here. We'll call that Z, just because I don't want to have S. It looks too much like fives when I write them. So we want Z, which I'll go ahead and denote is the length of shadow, just so we can remember that, since it doesn't quite start with that. And then we also want to know, so his length of the shadow when we are 10 feet from the base of the light. And so the other variable here is going to be the physical distance from the light post to us. And so both of those are changing. And so we can see that there's going to be some outcome, right? As we get closer, our shadow is going to either increase in length or decrease. And so I want to get a relationship between X and Z here. Once again, I can use similar triangles. And so I can compare the sides, the heights, 6 to 6, and that's going to be compared to X plus Z over just Z. Once again, cross multiply, and so I get 16Z equals 6 times X plus Z. All right, there is technically that relationship again, but there's definitely some more simplification that we can do here by distributing this out and then getting all my Z's on one side to just be 10Z equaling 6X. If you can, when you simplify, right, I know we didn't do it in this first one where we separated those out to get one variable in terms of the other. We left it there. That's okay. But when you can, it is beneficial to go ahead, especially if it works out nicely, where, like the second example, volume in terms of height. Here we have Z in terms of X. Even though they both have coefficients, we can leave those. Coefficients are easy enough to work with in the next step. Okay. There are some other situations that can show up, but like I said, there's really too many. If I went through every possible one, we'd be here for a couple hours, and I don't quite want to do that. And so stay tuned for the next video where we will walk through. Now that we have this relationship, we'll use a couple more steps and use the rates to answer the question.